Hi guys, this is Algebra 1, Topic A, Quadratic Functions. In this topic, we'll be able to question how can you use sketches and equations of quadratic functions to model situations and make predictions. If you look at the topic overview, we have 5 lessons total in this topic. We'll start with key features of a quadratic function, and then we'll look at different forms of quadratic functions, model, and then look at all linear, exponential, and quadratic models at the end. Okay, so topic vocabularies are parabola, quadratic parent function, quadratic regression, standard form of a quadratic function, vertex form of a quadratic function, and vertical motion model. So these are very important in this topic. Let's start with looking at the key features of a quadratic function in lesson 1. Okay. This is lesson 8-1, key features of a quadratic function. In this lesson, we'll be able to identify key features of the graph of the quadratic parent function. So important vocabs you need to know are parabola and quadratic parent function. So what's the difference between a quadratic function and a quadratic parent function? If you know what a parent function is, it is the standard function of the type. Okay, so if you have an absolute value function, the parent function without any transformation is just f of x equals absolute value of x, right? And then if you have transformations like slopes, the altitudes, right, and h and k, those are going to change your graph. But the parent functions are always the function, the pure function that does not have any transformation. So for a linear function, y equals x would be the parent function for a linear function. Okay. In the same way, f of x is equal to x squared would also be a parent function. But let's explore and reason and get started with the thought. Okay. So we're gonna look for relationships. How is the graph of f of x equals absolute value of x similar to the graph of f of x equals x squared? How is it different? Do you see any similarities or differences from the graph? Well, where are the directions of the arrows pointing? What are the vertex of them? Right? Those may be something that's similar, but obviously you have a straight line. You have straight lines for absolute value function. You have some curves. It's not exactly straight for the quadratic function, right? For the x squared function. So you can already visually see the differences and similarities. Let's record that. Okay, you can say both graphs open upward, have turning points, and have symmetry about the y-axis, right? The graph of f of x equals absolute value x is linear pieces. So it's a piecewise function, like as you have learned in topic 5. While the graph of g of x, or f of x, equals x squared is curved. So those are the similarities and differences. Part B. What do you notice about the axis of symmetry in each graph? What about the axis of symmetry? Are they the same? Are they different? What is the equation of the axis of symmetry? You can see that the y-axis would be the axis of symmetry for both graphs. What is the equation of this line though? It's a vertical line, so is it y equals 0 or x equals 0? Look at the points. Your y is changing, but your x is all 0, right? 0, 1, 0, 4, 0, 8. So this should be a line of x equals 0. So the axis of symmetry is x equals 0 for both graphs. Okay. So our essential question for this lesson is, what is the quadratic parent function and how can you recognize the key features of its graph? So these are the parent functions of the two different types of functions. Now we'll see more. And we'll see the key features of the graphs, okay? So example 1, we're going to identify a quadratic parent function. So what is a quadratic parent function? And how can we tell if they are quadratic parent functions? So first of all, there's your vocab. The quadratic parent function is an equation f of x equals x squared. So it's the simplest function in the quadratic function family. The graph of the function is a curve called a parabola. If you look at the table, when x is equal to -2, if you plug that into the function, -2 times the -2 is +4. So you have a pair, a coordinate pair of -2, 4, right? And so on, you have these points. So if you plot those points, you will see that, oh, the slope is not exactly the same. It's not a constant slope. The slopes will change, right? So it's not a linear line. You can't define it. You can't graph a linear line, but it does have a pattern, right? It is reflected across the y-axis. So if you just draw a nice little curve that goes through all the points, then you'll see, oh, it's going to be a parabola. And in order to describe that, you can use these words. The parabola opens up. So if it's a parabola that's going towards up, the upward direction, then the parabola is opening up, okay? And then the axis of symmetry is where the symmetry occurs. If you fold them in half, where is the line of the fold, right? The axis of symmetry is on the y-axis, which is, by equation, x equals 0. The vertex is 0, 0. That's where the lowest point or the highest point of your parabola is. The middle point, where it all starts, where the curve is at the maximum or the minimum, at the peak, right? Or the lowest point. So that is the turning point of the graph. Okay, so these are some characteristics. The axis of symmetry intersects the vertex and divides the parabola in half. Okay, so these are the major features that we can see in x squared function, which is a quadratic parent function. So let's look at try number 1. When are the values of f of x, the function, positive and when are they negative? So look at f of x. The value of f of x basically is y in linear function, in a linear equation where y equals x. But here, f of x is just your range, right? So when your range is f of x, right? Are the numbers positive? Yeah, look at all these numbers. It's all going to be positive. All these points have positive y's. When are they negative? Is the vertex negative? No, that's 0. It's not negative. So it's still going to be, it's all going to be greater than equal to 0, right? So are they ever negative? No. So what do you say? The values of f of x are always positive, except at the vertex where the value of f of x is 0. So let's write that down. There you go. So please make sure you know the vocabularies and the key concepts of the quadratic parent function. This is very important. And then we're going to start building up on this concept. Let's look at the next page. Example 2. Understand the graph of f of x equals ax squared. How does the value of the leading coefficient a affect the graph of f of x equals ax squared? So a, again, is called the leading coefficient. Okay, this is the leading coefficient. Why is it leading? We'll talk about it later. But this is for sure a coefficient, right? By definition, if you have a number in front of a variable that's multiplied in a term, that is called a coefficient. So let's graph some functions of the form, different forms. When a is equal to 2, we have the green line or green curve. When a is equal to 1, that's the parent function, right? 1 times x squared is just x squared. So your parent function is when a is equal to 1. When a is equal to 0.5, we have this blue parabola. So how are they different? How does a change the graph? Right? So when a decreases, so if it's less than 1 and it's a decimal, then it becomes wider, right? It gets wider. Because whatever your x is, and you square it, you divide that in half, because that's 0.5 is 1 over half, 1 over 2. And so it's going to grow slower. The y values are going to grow slower. So then your graph is wider. But then your green graph represents when a is equal to 2. So it speeds up the speed of the increase of your y values, right? So when x is equal to 1, 1 squared is 1, 1 times 2 is 2. So originally it would just be 1 comma 1, but then now it just boosts up to 2, right? And then if it's 2, if x is 2, 2 squared is 4, 4 times 2 is 8, so then it just goes up really quickly, right? So that's how it works. So for the parent function, parent quadratic function, when a is less than 1 but greater than 0, the shape of the parabola gets wider, okay? Gets wider than the parent function. When a is greater than 1, the parabola gets narrower than the parent function. Okay? So that was part A. Part B, how does the sign of A affect the graph of f of x equals ax squared? So sign, let's, instead of looking at the values, let's look at the sign. What happens if it becomes negative? Then all your values of y becomes negative. That means you can start at the same vertex, but whatever your value was, whatever the value of your y was, you have a negative one, negative value of that, right? So it basically reflects your parabola, your parent function, into over the x-axis, okay? So if you look at f of x equals 1.5x squared, that is the graph of f of x equals 1.5x squared. But if it's negative 1.5x squared, you have the same thing except it's mirrored across the x-axis, and your y values becomes all negative. So there are no positive values now, and the parabola flips over, and then it faces down. It opens downward. Okay, so this is a key characteristic. When a is positive, the parabola opens upward. So you're going to see this parabola. Okay, when a is positive. And then when A is negative, then it's not happy. Okay? So it's a frowny face. The parabola opens downward. So if it's positive, it's smiling. If it's negative, it's not smiling. It's frowning. Okay, that's a good tip for you to remember that. Let's look at try number 2. How does the sign of A affect the domain and range of f of x equals ax squared? I just kind of talked about it, so think about that and see how you can explain that. How does it affect? What does it do? And write it down, and we'll talk about it soon. So, the sign affect the domain and range? Does it affect domain? Does it change the possibilities of values of x? Well, is there a restriction then? Could it be greater than 1? Yeah. Could it be less than 1? Yeah. Could it be 0? Yeah. X could be anything. So it doesn't really change. X is still a real, like all real numbers, right? But does it change the range? Does it affect the values of y? Obviously, yes. Your values of y were positive when A was positive. Your values of y becomes negative when A is negative. Okay? So range is affected. Let's type that out. So the sign of A does not affect the domain, but when A is positive, the range is all real numbers greater than or equal to 0. And when A is negative, the range is all real numbers less than or equal to 0. So it does change the range. Okay, make sure you write this down in your note. Let's look at example 3. Interpret quadratic functions from tables. Over what interval is f of x equals 4x squared increasing? Over what interval is it decreasing? So do you remember the definition for increasing values and decreasing values? So if it's increasing, it goes up. Decreasing, it goes down. So when we're looking at when a function is increasing, we're looking at when x is increasing, y is increasing, that's increasing, right? So when they're going towards the same direction, when x and y are both increasing, then the graph is increasing. So if it goes up from left to right, that's increasing, okay? When it goes down, when the graph goes down from left to right, then it's decreasing. So when it's decreasing, as x goes up, as x gets bigger, y goes down. When y gets bigger, so it's going the other way, right? Then the x goes down. So they're going different directions. That is one way to remember it, but please remember that you're reading the graph from left to right, okay? Even if you're looking at a parabola that's facing to the left side, you're reading from left to right and see if it's increasing from left to right or decreasing. So even though if you look at this graph, from left to right, it is increasing. Although it looks like the arrow is pointing downwards, from left to right, the graph is still going up, right? So yes, you always have to read from left to right. Let's look at the function 4x squared. You're gonna make a table of values so that you can have some points to consider. So pick some random points, okay? When x is -2, y is 16. 4 times parentheses -2 squared would be 16. When x is -1, y is 4. When x is 0, y is 0, and so on. So if you look at the values, you probably have a parabola facing upwards, right? All your y values are positive. But then, as x increases, as x goes to the right, for negative numbers of x, your y is decreasing, right? So from left to right, this part of the graph is decreasing. And then this part of the graph from left to right, it's going up, so that's increasing. Okay, so you have to look at individual points and see if the values are increasing or decreasing from the x's point of view, okay? So the function is decreasing over the interval x less than 0 and increasing over interval x greater than 0. And why are we including 0? Because 0, 0, that's the vertex. And it's neither increasing nor decreasing. So it's just a vertex, okay? So you don't have to include 0. Everything other than 0 on the left and the right side of 0 is either increasing or decreasing. Okay, that's exactly where your direction of graph changes. Let's look at try number 3. A function of the form g of x is equal to ax squared increases over the interval x less than 0, so when x is negative, and decreases over the interval x is greater than 0, so when x is positive. What is a possible value for a? So it doesn't have to be exactly one answer, okay? We're looking for a possible value for a. There could be more than one answer, but try to come up with your own answer, okay? Think about it and write your answer and explain. Okay, are you ready? So, when it increases over the interval x less than 0, it means on the left side. So if that's the vertex point, on the left side of that graph of that vertex is going to be increasing. So it's gonna come from down towards up, okay? And then from the vertex, and that's where 0 is, okay? That's where 0 is. And from the vertex, when x is greater than 0, so on the positive side of x, the graph is decreasing. So it's going down like that. So it's probably looking like that. So it doesn't have to be a specific function. You just have to have a quadratic function that is opening downwards. So your answers could be anything where a is negative. So for example, if you have f or g of x is equal to negative 2x squared, then that would be possible. So it could be negative 2x squared, it could be negative 4x squared, it could be negative 8x squared, doesn't matter. Or negative 0.5x squared, it's still gonna be increasing when x is negative and decreasing when x is positive, okay? So make sure your a is negative so that your parabola is facing downwards, and that will be your answer. Now explain. Why is it? Because the graph is opening downwards, so the value of a must be negative if we graph that, right? Let's write that down. Okay, when we graph it, the graph is opening downward, so the value of a must be negative. Okay, let's look at example 4. Apply quadratic functions. The owner of a new dance studio is installing wooden floors in all of the dance rooms. How much should the owner expect to spend on flooring for a square room with 15 feet side lengths? So let's take a look at this information. So you can see that for each 15 by 15 floor, the flooring is on sale. And that's $8.75 per square foot. So square foot, what is a square foot? You have 1 foot times 1 foot, that is 1 square feet cubed, okay? So you divide this by 15, and then 1 cube here is 8.75. So 15 by 15, you figure out the area and multiply that by 8.75 to get the total cost, right? First, we're going to write a function so that it works for any area of dance floor in square feet. So let's say C of x, that's our function, is equal to price per feet square of flooring, which is 8.75, times the area of dance floor in feet square, which we don't know, so that's a variable of x squared. Okay? And then we're going to find the value of function when x is equal to 15. Okay? And so you just plug it in. 15 squared is first, and then you multiply that by 8.75. You get 1,968.75. So the cost for a new floor for a square dance floor with size of 15 feet would be 1,968. So 1968.75. $1,968.75. Okay. So if they want you to set up the equation, you need to be able to use a variable to represent the situation as an expression, okay? All right. So let's look at try number 4. By how much will the cost increase if the side length of the dance floor is increased by 2 feet? So instead of 15, we have 2 feet increase per side, right? So what's 15 plus 2? 17. Now we have 17 by 17 feet. Can you use the same equation? Yes, you can. Your x is just 17 instead of 15. Okay? So figure this out by yourself and see if you can get it correct. Come back when you are ready to check your answer. Okay, are you ready? So use the same equation. C of x is equal to 8.75 x squared. And your x is 17 now. So 8.75 times 17 squared is 8.75 times what's 17 squared? 289. Times that together. And finally, you will get 2,528.75. And that's your final answer. But actually, that's not your final answer. Because what does the question ask you? It's asking you by how much will the cost increase? It's not asking you how much would it cost, right? So that's how much it would cost for the floor that has a side of 17 feet per side. But how much would it increase? So now we have to subtract them. So don't forget to subtract the numbers. 2,528.75 minus 1,968.75. How much did it increase? 0.065. Okay, so 560. It increased by 560. So we can say the cost of the larger floor is $2,528.75. So the cost increases by $560, and that should be our final answer. Okay? All right, check your answers. If you didn't subtract them to get the final answer, then you didn't get full points. But $560 would be correct. All right, one last example, and we're done with the lesson. Let's compare the rate of change in example 5. How do the average rates of change for function f of x is equal to 0.75x squared and g of x is equal to 1.5x squared over the interval 2 less than or equal to x. So x, when it's greater than or equal to 2 and less than or equal to 4, compare. Okay? So we're looking at a limited domain. Okay? We're looking at the interval. So we're going to first graph two functions. Okay? You know how to graph. Make a table of values, put the points, and then graph it. Put a curve that goes through all the points. Okay, and then you'll see when x is 2 on 0.75x squared function, so f of x function, which is the red one, it's going to be 3, right? 1.5 times 2 squared, so 4 is going to be 3. Wait, 0.5. So that's f of x. Yeah. So that's 2 comma, there's 2 comma 3. If x is 2 for g, then g of x when x equals 2 is 6, right? So you have 2 comma 6. So that is where your interval starts. When x is equal to 2, that is your minimum value. So we're going to start here, right? And then 4, that would be your maximum value for x in that interval. So figure out what the y values are for 4 as well. You have 4 comma 12 here, and then 4 comma 24 here. So if you look at this interval from 2 to 4, right? You see the graphs, right? How does it compare? So this would be a red line, that could be a blue line. From this interval, how does the graph compare? Which one is increasing faster? Obviously the blue graph, it's very steep, right, compared to the red one. The red one is comparatively increasing slower, but they're both increasing, right? So that's how you compare. On average, the values of function f increases by, you want to find the slope through the interval. So yes, you can find the slope using the endpoints of the interval, but does that necessarily mean your lines are straight? No. But that's okay. You're just finding the slope using the two endpoints. And it's not an accurate slope because obviously it's a curve, not a straight line. But over that interval, the slope could be represented as a constant number. Okay. So looking at your points, use the slope equation. If you remember the slope equation, m is equal to change of y over change of x, which is y sub 2 minus y sub 1. X of 2 minus x of 1 with the 2 points. Okay, so looking at the slope, your f of x increases by 4.5 per 1x. Your g of x increases 9, so that you can really see by numbers how fast g of x is increasing compared to f of x. So use the slope over the interval in order to compare them. So on average, the values of function f increased by 4.5 units. So this is on average. It's not exact amount because obviously it's a curve. But if we find the slope with the two endpoints, that could be our average over that interval. Okay? And the values of function g increase by 9 units for each unit increase in x over the interval 2 to 4. So look at the question again. When they ask you, how do the average rates of change for this and this over the interval compare? If you see something like that, you want to figure out the endpoints for the interval. Okay? find the endpoints of the interval, and then find the slopes with the endpoints, and then that is your average rates of change. Then compare, okay, using the average rates of change, okay? That's how you get average rates of change. Rate of change is basically equal to slope. This is really, it just really means slope. So average slope is what we're getting, okay? Let's look at part B. How do the rates of change relate to the values of A in the functions? So let's look at the average rates of change. Let's look at our average slopes, 9 and 4.5. Are they related to A? Let's look at f of x. Your f of x is 0.75x squared. 4.5 is our average rate of change. And then you see A in g of x, which is 1.5. And you see the average rates of change for g of x is 9 over this interval. So what can you conclude? If your A is less, then your average rates of change is smaller. If your A is bigger, then your average rates of change is bigger. So that's how they could be related, right? So for positive intervals, so we don't know about the negative intervals because the negative interval would be decreasing, not increasing. So it would be flipped the opposite. The greater value of A, the greater the average rate of change. So in this case, the ratio of the A values in the two functions is the same as the ratio of the average rates of change. Let's look at try number 5. How do the average rates of change for f of x equals negative 0.5x squared and g of x equals negative 1.5x squared over the interval negative 5 to negative 2 compare? So now we're looking at the negative intervals, and we're looking at negative quadratic functions where the graphs should be looking downwards. So let's look into that. You may find it easier to graph and then figure out the endpoints. But if you don't need a visual graph in order to understand, then that's fine. You can get straight to the points of the endpoints and then figure out the average rates of change and figure this out. But please stop the video, pause the video, and figure this out by yourself and come back when you're ready for answers. Okay, are you done? So what is the first step? You want to figure out the endpoints, right? How do you figure out the endpoints? You can make a table of values, or you can literally substitute your values in your functions. So when x is negative 5, your f of negative 5, your function f of x will be negative 0.5 times negative 5 squared, which is negative 0.5, 25 times 25, and then that's negative 12.5. Okay, what about, so that means you have a point, negative 5 comma, negative 12.5 for f of x. Okay, what about g of x? G of negative 5 would be negative 1.5 times negative 5 squared, which is negative 1.5 times 25, which is negative 37.5. So your point for g of x would be negative 5 comma negative 37.5. Okay, do the same for x is equal to negative 2, because we just found the endpoints for negative 5. Now we just need the endpoints for negative 2, the maximum points, right, or the minimum points. So when x is equal to negative 2, f of negative 2 would be negative 0.5 times negative 2 squared, negative 0.5 times 4. So 4 divided by 2 is 2, negative, so negative 2. You have negative 2 comma negative 2 for f of x. And then g of negative 2 is equal to negative 1.5 times negative 2 squared. That's negative 1.5 times 4. And so 4 times 1.5 should be 5? Or 6, yes. So negative 6. Negative 2 comma negative 6 is another one for g of x. So then, number 2, find the slope for the endpoints, and that would be your average rates of change, right? So for f of x, we're gonna have these 2 points, negative 5 comma negative 12.5 and negative 2 comma negative 2. And that's gonna be, that's x, that's y, that's x, that's y. Let's put first and second points. So negative 2 minus negative 12.5 over negative 2 minus negative 5. And that would be 12.5 minus 2, so 10.5 over 5 minus 2, 3, right? So for f of x, your rate of change is 3.5, okay? And then g of x, your slope, let's use a different color. For g of x, we're using this one and that one. So your slope should be negative 6. So label your points just in case you mess it up. Negative 6 minus negative 37.5 over negative 2 minus negative 5. And that's equal to 37.5 minus 6 will be 31.5 over 5 minus 2 is 3. And so that would be 10.5. Okay? So now we have the average rates of change. Average rate of change for G is 10.5. And average rate of change for F is 3.5. So you can see that this is already 3 times the average rate of change for F. So how do they compare? We can simply say that the average rate of change of f of x is this. Average rate of change for g of x is that. And g of x is 3 times as great as f of x. Okay? There we go. And that should be our final answer. Okay, so make sure when they ask you to compare the average rates of change, you figure out over the interval, you figure out the endpoints using the interval. Okay, these are the endpoints. We're only looking at these intervals. And then you figure out the slopes for each function, and that would be your average rate of change for each function. And then you compare those numbers, okay? By graph, if you look at the graph, why are the average rate of change positive? It could be negative if the graph is decreasing, right? Because the graphs will look, they'll face downwards, okay? So if they face downwards, if you look at negative intervals, we're probably cutting here, right? So they're going to go up from left to right. So they're still increasing over this interval, okay? So your slopes are positive. So it will help you if you graph it visually, because you can visually see the graph and make connections how the interval is going to look over that interval, how the graph is going to look over that interval. Okay, so I would greatly recommend graphing them before you solve it algebraically. Then you'll be able to understand the whole picture. All right, that was our last example. Great job going through your first lesson of topic 8. Let's summarize our lesson. So the features of quadratic function f of x equals ax squared is that when a is positive, it and it's less than 1 and greater than 0, then the graph gets wider, right? So when a is greater than 0, less than 1, it gets wider. When a is greater than 1, then it gets narrower. But then when a is negative, so less than 0, then it is opening downwards. Okay, so when a is even if it's opening downwards, if the magnitude of a, so absolute value of a, is greater than 1, it gets narrower. So if you look at this, the magnitude of a, which is 2 here, that's greater than 1, so it's still getting narrower down. But it's facing downwards because it's negative. Okay? When magnitude of a is between 0 and 1, then the graph is wider. Okay? That's how it visually looks. If you want to understand, you need to look at individual points and look at the tables of values. Okay? So one last thing, f of x equals x squared without any transformation, any coefficient, that is your parent function. Okay? So you'll always be able to compare parent function when there's transformations of functions. All right, so that was lesson 8-1, key features of a quadratic function. If you have any more questions, please feel free to ask us. Otherwise, we'll continue in the next lesson, in the next video. Bye.